many problems in business, economics, and science that can be solved by finding an optimal amount of something, whether that be profit or population of a certain type of wildlife or what have you. The solutions to these problems are limited by things called constraints. In manufacturing, constraints might be things like the tax rate, the availability of skilled workers, and so on. We can solve these problems using a process called linear programming, in which the constraints are graphed, and then the thing that is to be optimized, called the objective function, and then the thing to be optimized, called the objective function, is graphed over the feasible region defined by the constraints. Let's take a look at this process. I'm going to start with a series of inequalities. 3x plus 2y less than or equal to 6. Negative 2x plus 4y less than or equal to 8. X plus y greater than or equal to 1. And x greater than or equal to 0. And y greater than or equal to 0. In many situations, we're going to have these last two just because we don't want to deal with negative numbers in business, in wildlife population, and so forth. So let's graph these. I'll start with this first one, 3x plus 2y. This is going to have a y-intercept of 3. And I'm going to let these each two blocks represent one unit. So my y-intercept would be there. X-intercept would be at 2. So 1, 2. So there's my line. And I want this to be less than or equal to 6. So I'm going to shade this direction. In my second inequality, I have a y-intercept at 2. So 1, 2. I don't have an x-intercept in this first quadrant area, but I do know that my slope is going to be positive 1/2. So up 1 over 2, up 1 over 2, up 2 over 4. So that's the line for that constraint. And we want to be less than 8. So again, choosing 0, 0, that'll make it true, so we know that we've got to go this direction. My third constraint, x plus y greater than or equal to 1. Both the x-intercept and the y-intercept are at 1. And greater than means we're going to go this way. So what's the area that's going to contain all three of those inequalities? I can see it's going to be on the y-axis here, x-axis here. Follow this red line and the blue line there and the purple. So that's the area of my feasible region. And I'm going to just erase the rest of this to make that a little more clear. That's my feasible region. Now we're going to look at an objective function to go with this. And my objective function is z is equal to 2x plus 5y. And I want to optimize this, which usually means I want this to be a maximum. So within this area, what values of x and y would give me a maximum? Well, I could pick values all day and not hit it. So there's got to be a little more reasonable way to do it. Let's say, for instance, that we want, let's try z equals 0. For z to equal 0, negative 2x would have to equal 5y. So if I divide by 5, so this gives me, after I divide by 5, y equals 0.4x, and this is negative. Because there's no y-intercept here, I know that this goes right through the origin. It has a negative slope, so it's going to come down something like this, and it's never going to touch my feasible region. So that's not going to work. Let's try a different value for z. Let's let z equal 5. If z equals 5, then I have 5. I'm just going to move the 2x over. 5 minus 2x equals 5y, and then divide by 5, and I get y equals negative 0.4x, and a 1 there. And you might notice that negative 0.4x is the same slope we had before. So we're going to be plotting a parallel line. My y-intercept is at 1. So right here, negative 0.4 means down 2 over 5, or down 2 over 5, like this. So that's the, let's get rid of this. That's one of the intersection points. Okay, so I could use this point maybe of y equals 1, x equals 0, among other points that would fit this. Let's see if we can find another one. What if z equals 10? For z equals 10, I'm going to have 10 minus 2x equals 5y. And then when I divide by 5, this would be 2 minus 0.4 x equals y. And so 2 on this graph would be up here for y-intercept, and down 2 over 5 would be there. So this line would be there, and you can see that the blue line and the red line are parallel to one another. And we're getting up toward the top of the feasible region, but we're not quite there yet. So let's try one more with z equals 15. If z equals 15, I'll have 15 minus 2x equals 5y. So I'll have 3 minus 0.4 x equals y. And so that would be up here. And we'll go down 2 and over 5. Now I've gone too far. Now I'm completely outside the feasible region again. So z equals 5 is an option. Z equals 10 is an option. Z equals 0 and z equals 15 are not options because they do not intersect with my feasible region. So how do I find my maximum value for z? I know that it's less than 15, greater than 10, and it's right here. And the question is, where is right here? What is that? Well, let's go back to our original constraint and see if we can find that point. Okay, we're going to look at not these two. I don't need this one, that's down here. But I want to look at these two inequalities and see where they might intersect. And I'm going to change them to equations because I'm really only interested in the borders. Okay, it looks to me like multiplying this one by -2 might be a good choice to get rid of the y's. So -6x, -4y, and -12. And now I can add this equation and this equation. -8x, these cancel out, and 8 and -12 gives me -4. Divide by -8, and we get that x equals 1/2, which looks pretty reasonable. That would be right about here. I'm going to put that into the original equation. Let's do 3 times 1/2 plus 2y equals 6. Well, this is going to be 3/2, so I'm going to subtract 3/2 from both sides, which gives me 2y equals 4.5, or 9/2. Divide by 2, and I get y equals 9/4. So this point is at 1/2 9/4. Okay, now what's the value of z at that point? Remember our objective function, z equals 2x plus 5y. So we're going to have 2 times 1/2 plus 5 times 9/4. Well, this is 1. That's easy. This is 45/4. So I could change that to 11 1/4, or 11.25. So I'm going to have 12.25. This is my optimal value for z. So that line would come right through here. It would be parallel to all the others. And that's my maximum value for z. If I wanted to find a minimum value for z, looks like it would be down along here. If I made a line parallel to the blue line, not parallel to the purple, but parallel to the blue, that went through this point, the values would be x equals 1, y equals 0, so z is equal to 2 times 1 plus 5 times 0, or just 2. So my possible values for z are from 2 to 12.25. Pause the video now and work on checkpoint 1. Before we go on with example 2, I'd like to introduce you to the corner point theorem, which says that if the feasible region is bounded, which means it's completely enclosed, the max and minimum values of the objective function will occur at corner points. So at one of the corners of the feasible region we'll have a max, and at some other corner possibly have a minimum. But this again only works if the feasible region is bounded. So let's practice creating a feasible region. So the corner point theorem can save us a lot of trial and error trying to pick values for z by drawing the objective function through the feasible region. We just have to know what the corner points are. So work on checkpoint 2 to get some practice at finding corner points. Before we get into another example, let's go over the procedures for finding an optimal solution. First thing we need to do is to write out the objective function and all the constraints. Sometimes these may be given to you, sometimes you'll have to develop them from the information in a problem. Second step, graph the feasible region. Third step, find the coordinates of all the corner points of the feasible region. Step 4, if the feasible region is bounded, then we know that the corner points are going to provide the optimal solution. Whether that optimal solution is a maximum, like for profit, or a minimum, as it might be for cost. So we're going to check the corner points to see which one gives the optimal solution. If the feasible region is not bounded, and both the coefficients of it are positive, then we know that the minimum solution is at a corner point, and there's no maximum. Now we'll use these procedures to work on another example. So I'm going to just sketch a feasible region. 3y minus 2x greater than or equal to 0. Y plus 8x less than or equal to 52, y minus 2x less than or equal to 2, and x greater than or equal to 3. Those are my constraints. So let's see what that gives us. Okay, I'm going to start with the easiest one. X equals 3, or x greater than or equal to 3. So that's just my vertical line here. And it would be shaded this direction. So this one's done. Now let's look at y minus 2x less than or equal to 2. I'm going to move the 2x over to the other side, so I've got y less than or equal to 2x plus 2. So I know that that's got a y-intercept at 2 and a slope of 2. So it's going to come up like this. And we have the y less than that. So that's going to be down this way. And that one's done. Okay, on this one, I would have y less than or equal to 8x plus 52. Okay, that's a very high y-intercept, but that line would come down, let's see, 5, something like this. And then y is less than, so it's going to be shaded this way. And then we haven't done the first one, which I could rewrite as 3y greater than or equal to 2x, and then divide by 3. So this one comes out of the origin and has a slope of 2 over 3. So it's going to look like this. And we have y greater than, so that's going to go this direction. So let's take a look at our feasible region. Okay, some of these points are not difficult to find. Some of them are going to be a little more challenging. For instance, this point is 3, 2. This point is going to be 3, 8. And then the other 2 points that aren't on that vertical line, we're going to have to solve either algebraically or graphically. I would recommend algebraically because the graph's just not going to be accurate enough. So let's look at 3y minus 2x equals 0, and y plus 8x equals 52. So I'm going to multiply this top equation by 4, which will give me 12y, negative x, and the 0 would stay the same. So now I have 13y, the x's cancel out, equals 52, which means that y equals 4. Put that back into one of my equations. 4 plus 8x equals 52. X is 6. So that's another point for me. 6, 4. And then the last one, we need to look at y minus 2x equals 2. And y plus 8x equals 52. So again, we're going to multiply by 4. So now I have 4y, and y is going to give me 5y. Negative 8x and 8x are going to cancel out. 4 times 2 is 8, plus the 52 is 60, so y equals 12. And then we can put that back in our original equation up top here and have 12 minus 2x equals 2. So negative 2x equals negative 10, and x equals 5. So this is my last point, 5, 12. So I've graphed my feasible region. I found its corner points. My feasible region is bounded. It's in the first quadrant. And so now I'm going to find values for the objective function. I didn't give you the objective function earlier. It's z equals 5x plus 2y. Okay, let's try them out. 3, 2. Well, 3 times 5 is 15. Plus 2 times 2 is 4 more. So for this one, we get a value of 19. Okay, for 3, 8, I'm going to have 15 again, but this is going to be 16, so this is going to be 31. So if I'm looking for a maximum, it won't be this one. But let's try these other two as well. 6 times 5 is 30, plus 8, so this one's 38. 5 times 5 is 25, plus 24, so this one's 49. So if I'm looking for a maximum value for my objective function, there it is. If I happen to be looking for a minimum value, I would choose this one. So pause the video now and work on checkpoints 3 and 4. Let's work another linear programming problem all the way through. We're going to start with our objective function, z equals x plus 3y. And this time I want to minimize. Okay, and my constraints are 2x plus y less than 10, less than or equal to 10, 5x plus 2y greater than or equal to 20, negative x plus 2y greater than or equal to 0, and then x greater than or equal to 0 and y greater than or equal to 0. Okay, I'm not going to draw these on. We'll just call this the x-axis and the y-axis and know that everything else has to fit in here. So let's look at this one, 2x plus y less than or equal to 10. I can move the 2x over and have y has to be less than or equal to negative 2x plus 10. So my y-intercept is going to be at 10. My slope is negative 2. So I start here and come down this way. And for y to be less than, I'm going to be shading this direction. When I look at this problem, I think solving by intercepts is a good idea here. If I let x be 0, then y is going to have to be 10. So when x is 0, y is 10. So it matches up with the first point on the purple line. If y is 0, x will be 4. So that'll be here. So I'm going to have a very skinny feasible region in there. Because if I let x and y both be 0, this would not be true. So this is going to be shaded this direction. So now my shaded area is in between the red and the purple lines. And I'll just put a red mark here so we know that that's the red line. And then my last point, or last line, negative x plus 2y greater than or equal to 0. Well, if x and y are both 0, this is going to be 0, so I know that 0, 0 is one of my points. And if I move the x over, then I have 2y greater than or equal to x. So y is greater than or equal to 1/2 x. So a slope of 1/2. would come out this way. And I have y is greater than that. So this is my feasible region. Just in between these two lines and above the blue one. Okay, so I'm going to let those go for now. And I'm asked to minimize, and I was told that minimum value is going to be at one of the corners. Now this is a very nice problem because two of the corners are pretty easy. This corner is at 0, 10. This corner I can see pretty easily is at 4, 2. Which means the only corner I still have to figure out is this one. And that's the intersection of 5x plus 2y equals 20 and negative x plus 2y equals 0. So it seems very obvious to me that I need to just change the signs on this one, which gives me 6x equals 20, or x equals, let's say 10 over 3. Does that seem reasonable? 1, 2, 3, and a third. Seems reasonable. So now I'm going to use that 10 over 3 minus 2y equals 0. So I'll move the 10 over 3. So I've got negative 2y equals negative 10 over 3. So y must equal negative 10 over 6, or I could reduce that to 5 over 3. And it's positive because I divided by a negative number. So 5 over 3 would be 1 2/3. And again, that looks pretty reasonable. So my third corner point is 10 over 3, comma, 5 over 3. So now I've got my corner points. Which one's going to give me the smallest value for this? I'm going to choose this one because it's closest to the origin. Try that first. So that would be 10 over 3 plus 3 times 5 over 3. So that would be just 5. So this is going to be 8 and 1/3. That's for this. Let's draw the arrow over here. That's for this point. For 0, 10, I'd have 0 plus 3 times 10 is 30. Well, that's definitely not going to be the minimum. It's much larger than 8 1/3. And so my other choice is 4, 2. So I've got 4 plus 3 times 2. So this is 6 and 4 is 10. So close, but not quite. Here's our winner. This is the point that minimizes the value of the objective function. Pause your video now and work on checkpoint 5. I know these problems are long. We're going to work one more and then we'll be done. This time I want to minimize z equals 2x plus 4y. And my constraints are x plus 2y greater than or equal to 10, 3x plus y greater than or equal to 10. And then x greater than or equal to 0 and y greater than or equal to 0. So again, we'll just use the edges of our graph for these two and work the other two in the first quadrant. So for this one, if I let x be 0, then y is going to be 5. So that point would be right here. If I let y be 0, then x would be 10. So that's right here. So there's my line. And if I let x and y both be 0, then I have 0 greater than 10, not true. So the origin is not in my region. I need to go this way. Now let's look at 3x plus y. Again, if I let x be 0, this time y would be 10. And if I let y be 0, x would be 3 1/3, about here. And there's that constraint. Again, if I let x and y both be 0, this would not be true. So that means I'm going to have to go this way. And I'm done. That's all the constraints I had. This is not bounded. But we do have corner points at 0, 10 up here. We've got this corner point. Let's just call it A for now. And then I've got a corner point here at 10, 0. So I need to find this corner point that I'm calling A. So I'm going to let these two things equal each other. They're very nice to me. And let both of them equal 10. So I can just write it. I have x plus 2y equals 10. And 3x plus 1y also equals 10. I'm going to multiply the second equation by -2. So 3 becomes -6. 1 becomes -2. And 10 becomes -20. So when I add this, I'm going to have -10. The y's will cancel out. I have -5x. So if -5x equals 10, then x equals 2. And I'm going to put 2 plus 2y equals 10, or 2y equals 8, so y is 4. So this intersection point is at 2, 4. So obviously not drawn great. A little more like that. So now I have my third corner point at 2, 4. And they did ask me to minimize this. So let's do that. If I choose 0, 10, I'm going to have 0 plus 4 times 10 is 40. So for 0, 10, I have a value of 40. For 10, 0, I'm going to have 2 times 10 is 20, plus 4 times 0. So for 10, 0, I have a value of 20. And now let's see what we get for 2, 4. 2 times 2 is 4, and 4 times 4 is 16, so this is also 20. Okay, so in this case, I have 2 points, 10, 0, and 2, 4. So this point and this point are both minimum values. And actually any point along this line between them, the two of them, would also produce a minimum value. Pause your video now and work on checkpoint 6.